7.3, and it's on things called partial fractions. Now, here's the idea. The idea is simple. We all know how to add two fractional terms. For example, I could add 2 over x minus 3 plus 3 over x plus 3 over x minus 1. If not, you should know how to add those fractions together. What do you have to have? You have to have that common denominator. So we're going to do this in reverse. I'm showing where the idea comes from. This is not what we're going to be doing. We're going to be doing the reverse of this. So I know my denominator over here is going to be x plus 3 times x minus 1. I have to have the same common denominator. To do that, however, I have to multiply top and bottom of this one by the opposite, x minus 1 and x minus 1 over here. So what do I have here? I have 2 times x minus 1. Okay, plus, similarly over here, I have to put in the factor of x plus 3, top and bottom. So what do I have? Plus 3 times x plus 3. Now if I multiply everything out, so I get 2x minus 2 plus 3x plus 9. All over, I get x squared plus 2x minus 3. Combine everything up here, 2x plus 3x gives me 5x. Negative 2 plus 9 is 7 over this. So that's how you add two, if you will, fractions together. Partial fraction decomposition goes in the reverse order. We are given a rational expression, and we'd like to write it and decompose. It's also called partial fraction, and it's also called decomposition. Because I'm going to decompose this into, and I want to end up with this. I want to start with that and end with my original 2 over x plus 3 plus 3 over x minus 1. Now, there are several different cases. This is a simple one. There are some that are much more complicated. Now, this becomes very critical in calculus, towards the end of calculus 1, when you're doing integrals. And you want to get them in things like this. Then those integrals are simple, where this integral is very complicated. So this is a skill, an algebraic tool that you'll use in the calculus. So we want to give you some exposure to it now. So when you get there, you can focus on, okay, I know how to do this. Let me then focus on the integral that I'm doing. A new thing. You don't know what it is just yet, but I'm just telling you, it is something that will be used in the calculus. But the idea starts by, I know how to add two fractions together and get a single rational expression. So I can add two rational expressions and get a single rational expression. But can I take a complicated rational expression and decompose it into two? And sometimes there's actually more of those. And there's all different sorts of cases that you have to consider. So this can be complicated. But that's the idea. So this is our case one, motivation for case one. We have something that's relatively simple. So let's take a look at an example of how we would do that. This is case one. Then I'll look at some of the other cases, because sometimes you can't always factor those expressions. So it's not always possible to factor them as easily. And then you get what we call the irreducible quadratics. And we have to do something separate with those. So this is all what we call case one. Something we will be able to factor. And say I have the following. I have 2x minus 5 all over x squared plus 2x minus 8. And I want to see if I can rewrite that in its decomposed form. First step over here is an example. I would factor the denominator here. Okay, so I leave that as 2x minus 5 all over, and I have an x plus 4 x minus 2. Now, the other thing you're going to notice, this is 1 degree less. Case 1, that can't be the same degree as this. This is like 1 degree less than the other one. I can't have a square there. I could have a constant there. Constants are possible, but I just can't have a square term. Can't have anything equal to that over here. So once I do this, then the assumption is, because we just worked a problem similar to this, that it could also be written as in this. We could take some number a, I don't know what a is, that's by undetermined quantity, over the first factor, plus b over the second factor. So this is my first step, there's my second step. Now what do? So I now have this, and I want to find and solve for a and b. So this third step is I'm going to multiply, I have this equation right here. I'm going to multiply both sides by x plus 4, x minus 2. Let me show you, I'll do that. So I have, on this side, I have 2x minus 5. In the future, you'll see the shortcut, and you'll do the shortcut. But for now, let me show you what you're actually doing. Okay, so this is my step 3 I'm going to perform here. I'm going to multiply everything through by x plus 4, x minus 2. Everything over here. And then simplify this. What happens over here? Everything here cancels. So the left-hand side, I simply have the numerator of what was there before. Over here, the x plus 4 cancels. So what do I have? I have a times x minus 2. Over here, the x minus 2 cancels. So I have plus b times x plus 4. Okay, so that's my step 2. Step 3, what I do is I multiply everything out over here. I mean, step 4, excuse me. I multiply everything out. That stays the same. So I have 2 times x minus 5 is equal to a times x minus 2a plus b times x plus 4b. Okay. Then notice I have x terms and I have constant terms. So then what do is I put like terms together. It's all about like terms now. So on the left-hand side, there's nothing to change, but over here, I can add the a and the b together. So that's a plus b times the x. And then over here, I have minus 2a plus 4b. Okay. Now, I want the left-hand side and the right-hand side to be identical. So I have to have the same coefficient in front of the x and the same constant term. So this gives me 2 different equations. One equation tells me a plus b has to be 2, because that's the coefficient in front of the x. Okay. It also tells me that negative 2 times a plus 4 times b has to be equal to the constant term, -5. Look what we have, a system of equations. See if you can do step 7 and solve that system. This for A and B. So take that and solve that for A and B and see what you get. That's what I want to do a little bit today. We'll go over it some more on tomorrow, just so at least you have that. I remember what I put first. I think I put the x plus 4 first, so I think I did put that. You write it two different ways. Sometimes you write it just with that number up top, or sometimes you write it like this. Either way is acceptable. This is just writing it as a fraction, 1/6. Now, did anyone want to see how I got the solution? B is -1/6 and A is 13/6. Anyone want to see how I got that? Okay, let's kind of put that in. This is my system. That's back to what we did in chapter 6. Solving a system of equations. I think we're okay up to here. Let me rewrite the system. A plus B is equal to 2, minus 2A plus 4B is equal to -5. Equation 1 and equation 2. What I'm going to do, I'm going to leave equation 1 the same. A plus B is equal to 2. Multiply this by 2 and add it to that. So 2 times equation 1 plus equation 2, the A is going to be gone. 2A minus 2A, 0A. Multiply B by 2. I'm multiplying equation 1 by 2. 2B plus 4B gives me 6B. 2 times 2 is 4. Adding to -5, I get a -1. That enables me now to solve for B. So B is equal to a -1/6. Okay, what can I do with that? Well, I can use that in the first equation and now solve for A. So these are things that we've done in the past, and you should be able to go back and be able to solve these systems. So now I have A plus B. Well, B is a -1/6 is equal to 2. And what do? I add 1/6 to both sides, so I get A is equal to 2 plus 1/6. Well, let me turn the 2 into 6. That gives me A is equal to 2 is 12/6 plus 1/6. Well, 12/6 plus 1/6 is 13/6. So there's my A, and there's my B. Now, if I were to combine these two together with those coefficients, I would get that back. And you can verify that and show that. This is a complicated thing. It involves solving a system of equations. So that's what we did in chapter 6. Chapter 7, we're going to utilize that skill. You'll have this all the time. You typically, when here, you're going to have these two. If there's two of those factors, you'd have two of them. Now, this is case one is you have what we call unique factors. So case one, this deals with having unique linear binomial factors. That's case one. So for example, you could do something like this. Let's say you were already given it in factor form. Say you're given something like, x minus 2, x plus 3, x minus 1. Now I have three of them. This is going to be a cube when I multiply everything out, so I could have a square over here. So I could have a, x squared minus 2x plus, 1 or something. This is squared. This is 1 degree less. I could have just have it. It could just be a minus 2x plus 1. It could just be a constant 1. How is it going to be written? It's always going to be written some a over the first binomial factor plus b over the second factor plus c now over the last one. Now we're going to have a system of three equations and three unknowns. What would I do? I'd multiply everything by this, and it would just give me x squared minus 2x plus 1 is equal to a times x plus 3, x minus 1 plus b times x minus 2, x minus 1 plus c times x plus 3, x minus 2. What would I do? Multiply everything out over here. I get some coefficients in front of the x squared that involve a, b, and c. I get a coefficient in front of the x that involves a, b, and c and their multiples. And then I get my constant term at the end. I'd equate this equal to 1. That's the coefficient in front of the x squared. I'd equate this equal to negative 2. And I'd equate this equal to 1. What would I have? I'd have a system of three linear equations in terms of the unknowns a, b, and c. Gives me three equations, 1, 2, and 3, and the unknowns. This is a more challenging one. The other two parts were relatively easy. So we will go into this more tomorrow. I got a feeling the homework will probably go very quickly. Tomorrow is our shorter class, so we don't have that much to do. I'm not going to solve this one right now. It's a bit more complicated, but you can kind of see if you multiply this out, you can have an x squared, an x term, and a constant. You can have an x squared, an x term, and a constant, x squared, an x term, and a constant. You group all the coefficients for the x squares together, and they're going to involve multiples of a, b, and c. In essence, this one's going to be simple. The first one is just going to be a plus b plus c has to equal 1. So as long as you have unique linear binomial factors, you can keep on doing this. Now, if this is the same degree, well, then you have to, we're not going to do that, but when you get there, you have to do long division first, and then work it from there. But this has to be 1 degree less. Notice x times x times x would give me an x cubed. Has to be at least 1 degree less. If it's the same degree or higher, you have to use long division first to get it down to that case. But we'll keep it light and not that complicated. But this is a tool that you need to get proficient at. Okay, so it's the partial fractions. And we gave motivation for and a showing of case 1, if you will, where in the denominator you have unique factors. So you could have something that looks like this, say 2x minus 3 over x plus 4, x with 2x minus 1, whatever. These are all simple binomials, and they're all linear. The numerator is at least 1 degree less. It can't be the same. It has to be less than the degree of the number. It could be just a constant there too. We could actually work that out as well too. That's case 1. So in this case, the denominators are all unique factors. And how would I set it up? A over the first factor plus B over the second factor. And then solve it as we did that yesterday. Okay, not all of them are of that form. Sometimes you have a repeated factor. So this is case 2. You can have a repeated factor. So in this case, let's take a look at a specific example, and we'll kind of show you how to proceed with something like this as well. So in this case, I have minus 4x plus 5. This is what I mean by a repeated factor. You might have x minus 1 quantity squared. What is going to be the approach? Now I could give you the motivation for it. Let's just go right to how you're going to handle this. What you're always going to do is simply write this as some a over the factor without the repetition. So it's a over x minus 1, okay? Plus, and then you take a b, these are constants, over x minus 1 quantity squared. You always have to go up to that factor. And I could show you why, but in the interest of time, we won't. But there's a little bit in the textbook you can look at that. This will always work. Now, if this happened to be a cubed, then I'd have a c over x minus 1 cubed. You just keep carrying it forward. So this is what we're going to solve. So how do we solve it? Just like we did everything we did yesterday. I'll come through and multiply everything by the denominator over here. So this is the solution approach. So x minus 1 squared. Over here, these cancel out, so it gives me simply my negative 4x plus 5 on the left-hand side. Over here, I have this x minus 1 cancels with one of those, so it gives me a times x minus 1. Both of these cancel out to give me plus b. Very simple. Then I distribute everything over here. Ax minus a plus b. Then I organize those. You can see they're organized by their types. Let's qualify. This is my x term. I only have one x term over here, so that has to have the same coefficient. My constant is made up of the other two terms over here. So 5 is a combination of the a and the b on the other side there. So that 5 is equal to that. So this one's fairly easy. It tells me a then, over here, a has to be equal to a negative 4. And then what do we have? Well, we have the second equation, which says that 5 has to equal to be negative a plus b. Well, we just turned out that a is equal to a negative 4, so I can use that in here. So that gives me a positive 4. So that tells me then that b is simply equal to 1. So that means this rational expression is simply a negative 4 plus, oh, not this one, this one over here. This one is a negative, let me just write it over here. So I have negative 4x plus 5 over x minus 1 quantity squared, which is just equal to a negative 4 over x minus 1 plus a 1 over x minus 1 quantity squared. And you could combine these two together, meaning all I need to do is multiply the top of this by x minus 1 and the bottom by x minus 1, and I would combine them, and I would get the same exact answer. And you can see that it does work. So that's case 2. You have a repeated factor. Yes, Colin?
How did you get A and B? Numerical value of A and B?
Okay, so what do I have? After I multiplied everything by x minus 1 squared, it all clears out. And then it just gives me this equation. So this equation is what I have. One of the x minus 1's canceled here, the other one did not. Both of them canceled here. Now, this is a polynomial map, so let me distribute this. So what I have is I have two polynomials. Well, this is an equation. Let's look at it this way. Let's say if I moved all the x terms together. This is another way of looking at it. So I could move the 4 over if I wanted to. Let me just shut the noise out. So what I could do is, let's move everything on one side of the equation. This is another way of looking at it. So I'm going to move that negative 4x over, so I'm going to get a 0, and the 5 is going to come over. So that gives me a plus 4 times x. Now the a and then the plus 4. And then I have my b plus b minus a and minus 5. So this has to be 0. That means both of these have to be 0. To get 0 over here, I have to choose a and b, so the coefficient in front of the x is 0 and the constant term is 0. So this tells me a has to be equal to negative 4. Okay, so I know a is negative 4. This tells me b plus 4 minus 5 has to be equal to 0. Well, b, 4 minus 5 is minus 4. This tells me b has to be 1. Or I could simply just say that this x term has to equal that term, that constant term has to equal that constant term.
All right, and
does that make sense?
Able to do it like that with a repeated factor?
You're barely coming through on your mic. I don't know. Your mic maybe is set down. I can barely hear you.
So we'll always do that with a repeated factor?
Yes, and in certain cases you might have an x squared term. And the x squares have to be the same. The x's have to be the same. The constants have to be the same. So sometimes you could have an x squared over here. We'll see on some of the other problems very shortly. That's always going to be the case over here. Always the case. And you're always going to clear out. You're going to get rid of everything in the denominator. You essentially want to clear all this stuff out. So make it a simple linear equation rather than a rational equation. It's always the approach. And then you get a simple system. Now this was an easy system. Some of the other systems can be a little bit more elaborate. They could require some of the techniques that we developed in Chapter 6 for solving. Because sometimes you might have more than one constant. You can have a system of 3 equations and 3 unknowns, or 4 equations and 4 unknowns. It can get unwieldy depending upon the problem. But for us, we're not going to get too complicated. So let me give you one to try over here and see how well you can do. I'll just make one up. Try this one. We have 2x plus 3 over x plus 4 squared. See if you can set that up and find out what it looks like. According to this is a squared, so we know it's got to be a over x plus 4 plus b over x plus 4 squared. See if you can at least set that up and what you would do. one where you can sometimes just do these in your head almost. So I get A is 2 and B is -5. Anyone want to see how I got that? Is that working out? Okay, so what I do is I put everything over, my A and B. So this is what I have. I'm multiplying everything here by x plus 4 quantity squared. Cancels, cancels. One of those cancels, one of those, both of those cancel out. So that just gives me this equation here. What I can do is I can distribute the A over here. So I get 2x plus 3 is equal to, let's distribute that, A x plus 4 times A minus B. 4 times A, excuse me, for A minus B. Plus B, excuse me, plus B. Okay, now what do I need to do? I need to identify the x terms. Well, I have two x terms. That x and that. They have to have the same coefficients. So that tells me right away A has to be 2. Well, if A is 2, that is 8. So I have the second equation. 3 is equal to 8 plus B. Subtract 8 from both sides, and I get -5 is equal to B. There it is. Very simple system of equations to solve for that. That's not too bad. Now practice some of these. Okay, we have one more case. So the next one is our case 3, and that is something when we have the irreducible quadratic. That means something that we talked about earlier that does not factor over the rational numbers. So case 3 now one of the factors is an irreducible quadratic. So for this sort of case, we might have something that looks like the following. So we have 3x minus 4 over 2x plus 3. And now we're going to have our irreducible quadratic, x squared plus x plus 1. Meaning I can't factor this over, integer factors or rational number factors. In fact, its roots are imaginary. So what do? Well, we handle the unique one like we always do. So the unique factor has a single value over itself. It's just a over 2x plus 3. Well, how do I handle this? Well, what I'm going to do over here is I'm going to be putting a binomial on top, b times x plus c, over the irreducible quadratic. So anytime you have an irreducible quadratic, it's a x term and a constant term, where those are the undetermined coefficients. It's always that way. So if I had another one of these factors, I might have an a over this factor, b over the next one, and that might be cx plus d. It's always going to be that way. How do I solve this? Same approach. I want to get rid of all the denominator terms. So very simply, I multiply both sides of this by that denominator right there. So I multiply everything on this side by 2x plus 3 times x squared plus x plus 1. Do the same thing over here. 2x plus 3 times x squared plus x plus 1. Multiply everything by it. So these cancel out with everything down there. So it just gives me a 3x minus 4 over here, equal to. Well, what happens over here? Well, the 2x plus 3 cancels, but the x squared plus x does not. So I have a times that x squared plus x plus 1. Okay. Then I come over here and I multiply here, and the x squared plus x plus 1 cancels, but the 2x plus 3 does not. So I have plus bx plus c quantity times the factor that didn't cancel, 2x plus 3. Okay. Now let's multiply everything out and get the different like terms together. The left-hand side doesn't change. That's the side that I'm trying to emulate. But over here, I do get differences. I have a x squared plus ax plus a. Then over here, I multiply here, I get plus 2b x squared, I'm multiplying that times that. And then I'm going to have 3bx, and then I'm going to have 2cx, multiplying those, plus 2cx, and then c times 3 gives me plus 3c. Okay, let's combine, get the like terms together. What I see here is I see 2x squared terms. So let's put them together on the right-hand side. So that would give me an a plus 2b, just taking the coefficients, times x squared. Okay. Then I also have some x terms over here. There's an x, there's an x, and there's an x. So I can combine all those together. So I get plus, and I have my a plus 3b plus 2c. And this is all times the x. And then at last, I just have the constant term over here. I just have the constant term. I have my a and my 3c. So it's my plus, and I have my, I'll put in parentheses, but I don't need to, a plus 3c. So now I'm looking at the left-hand side. I have to mimic everything on that left-hand side. So here's my 3x minus 4. Now, if I wanted to, just so to illustration purposes, I could put a 0 times x squared, because there is no x squared over here. There's no x squared over here. So what do I have to be the same? Well, this coefficient has to be 0. That gives me one equation. A plus 2b has to be 0. Why? Because x squared must cancel out. This equation here has to give me 3. I have my a plus 3b plus 2c has to be equal to a positive 3. Then I have this equation here. That has to be my constant. So I have my a, plus 3c has to equal negative 4. I'll set this up more like an equation. And there's my system. I have a couple of zeros in there, it makes it a little bit easier to solve. But let me stop there. Does everyone see what I did and why I did it? Is that okay? I cleared out everything, and I have to have the polynomial on this side has to be the same as the polynomial on that side. That means their coefficients have to be identical. So that means that has to vanish. There is no x squared term over there. This has to be, the coefficient in front of the x has to be 3. That constant at the end has to be negative 4. Okay, see if you can take that now and solve that system. So solve that system and see what you get. Give you a minute to try that. several different ways of solving. Sometimes just substitution, solving one equation for, you could set it up and do the elimination method. But I would just, since there's 2 here, I might solve that for, A, remove the A, and then you can solve for the B and C. So this tells me, in this case over here, I could write A is equal to negative 2B. I could use that over here. So I have negative 2B plus 3B plus 2C is equal to 3. And do it over here. Negative 2B. And I have plus 3C. 4. Well, this is easy enough. This just gives me B. I can leave it over here. I don't need this. Just need my original problem, just so I can write it out in the end. So I can multiply this by 2 and add it to that if I wanted to. I could solve this for B and I could do substitution. However you want to solve. So many different ways of doing it. So this is going to be 4, 7, 6 minus 4 gives me 2. So I get 7C is equal to 2. So this tells me in this case C is equal to, I get C is equal to 2/7. Then I could come over here if I wanted to and find A, and then I could find B over here. Doesn't matter. So this I can solve this system, multiply everything here by 2, and add it to the equation beneath it. 4 and 3 is 7C. 6 minus 2 is, 6 minus 4 is 2. So 7C is equal to 2, so C is equal to 2/7. Come over here and then solve that, the C over there, so I end up with A. You can see you have to do your work over here, plus 3 times 2/7 has to equal a negative 4. So this is 6/7, so I subtract it, so I'm going to get A then. Do it down over here. A is equal to negative 4, subtracting 6/7. Negative 4 is negative 28/7. And negative 28 minus 6/7. That gives me a negative 34/7. And then, now that I have A, and then can come over here and find B. I could solve that for B. So B is simply equal to, if I put it, this is minus A over 2. Take the negative of A and divide that by 2. So in case B then is equal to a positive 17/7. So when all is said and done, so this is what you should be able to do. This is chapter 6. You should be able to solve those systems. And when all is said and done, this is my final answer over here. I'm saying that 3x minus 4 over 2x plus 3 times x squared plus x plus 1 is equal to, well, A over here is a negative 34/7 all over 2x plus 3, plus now my B is a positive 17/7 times x plus C, which is a negative or positive 2/7, so 2/7 all over x squared plus x plus 1. Now, if you wanted to write this a little nicer, you could write it this way. You don't have to. You could put a negative 34 over 7 to x plus 3 plus 17x plus 2 over 7 times x squared plus x plus 1. Either way is okay. Coefficients like that will bring down that 1/7 throughout everything. It's the same exact answer in the end. So you can see where they do get challenging. And this is going to be required when you get into Calculus 2 more so than anything else. And also you'll see it in Calculus 3 if you have to go that route. Partial fraction, the partial fraction decomposition is an extremely important thing. It involves a lot of analytical techniques, solving systems, understanding how we go from here to getting that system. It's a lot of steps to this process. Now, you can have several different cases going together. Well, I'm not going to make it that complicated on a test, but you could have something like this. And I'll just show you how we would set it up. And then you can see you can get a really large system of equations that could really bog you down in terms of what you're trying to do. Because you could have case 1, case 2, and case 3 all together in the same problem. And it could be really complicated looking. I'll show you how to set it up. We're not going to solve it because obviously it'd be very unwieldy. But you actually could solve it fairly easily on a computer. But now we have something more general. We are not going to see anything like this on a test. But you could have, let's put some factors. This is even more dramatic. This is, let's put it this way, 2, 4, 7, 8. I could have a 3. I could skip one. Let's skip 2. This is a real complicated one. We're not going to see anything nearly like this, but how would you write this? Okay. I want to make this a 4. I don't want to make that the same. So I have a single distinct 0. So I'd write that as an A over X plus 2. Okay. Got rid of this one. Yep, this is what nightmares can be made of. This is to the 3rd power, so I'd have to write this as a b over x plus 3 plus a c over x plus 3 squared plus a d over x plus 3 cubed. Okay, so taking care of that one. Then I'd have to move to this one. That's a plus an e over x plus 4 plus an f over x plus 4 squared. Not done. Then I'd have to take care of this next one. Well, that's going to be a fg times x plus h over x squared minus x plus 1. But I have to take it up to another level. Continuing, I'm going to get a ghi xi plus j over x squared minus x plus 1 quantity squared. So if the irreducible quadratic is squared, I have to do it just like I would if I had the binomial. So you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 unknowns. And you'd have an equation with 10 unknowns and 10 equations in which to solve everything. So it would kind of be a bit of a nightmare. And luckily, we're not going to see anything close to that. So usually, it's much more contained, very much constrained. But you can see the general idea. You apply case 1, case 2, and case 3 to everything as you go along. Okay, so let me give you one that's a little bit easier to work and see how well you can do on that. And this is the need for computers. With a computer, you can set that up and do it very quickly. So let me just give you an easier one to try. Now, the solutions may not be great. May not be, simple integer values, the A's and the B's and the C's, but at least you can make them work. So try that one. That's a simple one. That involves the case 1 and case 3 over there. Hopefully everyone sets it up correctly. And then, can you get rid of the terms on the bottom and make those work? And then hopefully you're going to see the equations that come out. There is no x squared. And that's how you solve it. We're not going to go through and solve it, but hopefully you see the process. And then you put in your value for A, B, and C. At least you can see the process. So it can be involved and it can be complicated sometimes. This is nowhere near as bad as that other one I put up, which would be a nightmare. You have to have a large board, a lot of paper to write it all out. But at least see the process. So I get my system of equations, which is I have A plus 2B is 0. Why is it 0? There is no x squared over there. Then I have my 4A plus 3B plus 2C has to equal 3. Why? Because there's a coefficient of 3 in front of the x term. Then I have my A plus 3C has to be 5 because that's what the constant term is. The constant term is 5. There's my system. Go and solve that. Very similar to what I had earlier, so a little bit different, but you're going to get some sort of coefficients for A, B, and C that way. So this case is obviously the more complicated one. If it's simply raising to a power, that's the easy case. If it's just, 2x plus 3 squared, that's a much easier case to deal with. So that's our partial fraction decomposition.